And I'm presenting a PPT on a paper from Keida Shihora and Toshihiko Yamasaki from University of Tokyo on self-blended images for generalizable deepfake detection. This paper is to propose synthetic training data and using self-blended images for deepfake detection. They are trying to build more general and robust detectors by training on some synthetic fake samples that consist of some forgery traces and which are difficult to recognize. As you know, deepfake technology has become increasingly popular, and they can create almost any fake images or videos, or in fact, or audios too, and can be used for any kind of malicious purposes. So it is very much important to detect this kind of fake, images and videos. So in order to, protect our privacy. Uh, this paper actually proposes a new method to detect these deepfakes uh, by generating self-blended images and using a deep neural network to classify. This paper is, making a self-blended images and trying to generate a synthetic data set for deepfake detection. They are actually trying to, get the same image and making a self-blended image so that they can give it to they can train into the model using that, and they can detect the the deepfake images. This method consists of three steps, which are pre-processing, then self-blending, and classification. So basically, in the pre-processing step, they try to convert the input image to the grayscale and facial, and then they detect the facial landmarks. And after that, they try to get the step two is the self-blending, and they try to self-blend the image and try to generate a self-blended image, which can be given to the neural network. The third is the classification, in which they are trying to build a neural network which can detect deepfake images. They tried different different algorithms like ResNet 50, ResNet 152, efficient net B1, efficient net B4, and they chose to go with efficient net B4, which achieved 99.6 for accuracy on FF plus. Scenario is like the source target generator, which is the STG, and the MG. They both receive the input, and the mask generator creates a blending mask from the facial landmarks, and then deforms it to increase the diversity of the mask. The STG generates, pseudo source and target images from the image which is given to them using some image transformations, and then they are finally combined in and with the mask, and then the self-blended images are self-blended image generation algorithm. If you want take a look, it basically takes in the image size image and the size of the image, and then the facial landmarks of the image, and then they give the output with the self-blended image. STG actually initializes that pseudo source and target images thereby copying an input picture. They randomly apply some kind of changes to either the source or the target in order to create some statistical discrepancies between them, and then they combine as I said, then they combine the source and the target photos to get the mask generate MG, which and MG, and then the MG uses the landmark detector and then forecast a facial region in the input and initializes a mask by computing convex hull and different facial landmarks. Then now in this paper they're evaluating they're trying to do two approaches, which is cross data evaluation and the cross manipulation evaluation. Sorry, yeah. Um, they're in the cross data evaluation. They're trying to train their model on FF plus and then evaluate on different state of the art methods, CDF like CDF, DFD, DFDC, DFDCP, FFIW, etc. And in cross manipulation, they are trying to evaluate the generality of their model on unseen manipulations methods on FF plus, DF, F2F, NT, etc. And then they report the video level area under the receiving operating characteristic curve to compare with the prior works. That's the AUC. There are four categories in this. They're trying to do the landmark mismatch, in which if they can find if there's a mismatch in the landmark. The second one is the blending boundary, if there's a blending problem in the boundary. The third one is the color mismatch if the colors are not matching, or the frequency inconsistency. Of this one is that it is very much least comparable to the state of the, it surpasses and very much least comparable to the state of the art methods on all test sets, especially on DFDC and DFDCP, where previous methods suffer from domain gaps and between the training and the test sets. The method outperforms the state of the art unsupervised baseline by 4.9 and percent and 11.78% respectively. The proposed method was evaluated on Syllab A, HQ, and deepfake detection technology, test challenge dataset. The results show that they got an accuracy of about 97.8 on Syllab A, HQ, and accuracy of 98.6 on D. The limitation of this preferred, there are two limitations, namely, the one is the use of facial landmarks, which is very much affected by different factors. So in future they can work on that. And also there's another limitation as in for this paper they can only they can only detect the self images, not the video. So in future they can try to work on the conclusion. This paper is trying to propose a new method to detect deepfakes by generating self-blended images and using a deep neural network to classify them. The proposed method very much outperforms the existing methods in detecting deepfakes, as demonstrated by the results on the Syllab AHQ and DFDC results.